Imagine being able to build a forest, but the trees are 1,000 times thinner than a single human hair. Or weaving ribbons so tiny they're completely invisible. This isn't some far-off science fiction. This is nanoscience. Today, we're going to be architects of the invisible, diving deep into the world of microscopic construction, and we're using the incredible work from Dr. Jinfeng Wang's dissertation as our guide to see how we can build, literally, atom by atom.
Just look at this. What you're seeing is not a drawing. It's a real image from an electron microscope. It might look like a dense forest, but each one of those trees is a perfectly aligned zinc oxide nanowire. They're grown on a special atomically flat surface called a mica substrate. Each one is a tiny, perfect crystal pillar in a city built on a scale that's almost impossible to wrap your head around.
And that really brings us to the biggest question of all for this explainer. How? How is this even possible? How do scientists get this level of godlike control to build these complex structures in a world we can't even see?
Well, to answer that, first we've got to understand the rules of this new world. And let me tell you, it's a place where pretty much everything you think you know about materials gets flipped on its head.
See, nanoscience isn't just about making things small for the sake of it. It's about studying materials at a very specific scale, the nanoscale, where the basic properties of matter itself begin to change. A material that's totally boring in our world might become an incredibly powerful catalyst. Something that's opaque might suddenly turn transparent. It's a whole new game. So just how small are we talking here? A human hair is about 80,000 nanometers wide. So we are operating in a realm that is thousands of times smaller than that. Here's a crazy thought for you. Your own fingernail grows about 1 nanometer every single second. That is the kind of mind-boggling precision we are dealing with.
And this right here is why it all matters. At this tiny scale, materials just unlock these amazing new superpowers. As you can see in this table from the research, their electrical properties get better, they start doing new things with light, and they can become way stronger mechanically than their normal-sized versions. We're literally unlocking a whole new toolbox for engineering.
Okay, so with the basics covered, let's get back to building. Our first stop in this little nano gallery is the most basic building block of them all, the nanowire.
I mean, just look at the incredible uniformity here. These zinc oxide nanowires are almost perfectly identical in their shape and their size. Now, for scientists, this isn't just pretty to look at. This is the whole goal. Creating structures that are this uniform is absolutely critical if you want to build reliable nano devices, whether it's for sensors or for new kinds of computer chips.
But how do you actually get from a simple chemical powder to this beautiful field of perfect crystals? What's the secret ingredient? How do you impose that kind of order on all that atomic chaos? Well, it turns out you need a sort of nano-construction foreman.
And here's the secret sauce, the catalyst. On the left, you can see what happens without one. You just end up with a messy, jumbled pile of zinc oxide particles. But on the right, by adding a tin catalyst, those exact same atoms are guided into forming these perfect wire-like structures. The catalyst basically acts as a seed, a starting point for the whole thing to grow.
The process Dr. Wang used is called thermal evaporation, and it's actually elegantly simple when you break it down. First, you just heat the source material, the zinc oxide, until it turns into a gas or a vapor. Then, a carrier gas pushes that vapor over to a cooler area. Third, these little catalyst particles that are sitting on the substrate, they act like tiny magnets, and they collect that vapor. And finally, as more and more vapor collects on that catalyst seed, it crystallizes and grows upwards, forming one of those perfect structures.
Okay, so let's move on to our next exhibit and see how this all builds on itself. Because once you can make a one-dimensional wire, the next logical step is to make a two-dimensional ribbon.
And here they are. These are zinc oxide nanobelts. They are still unbelievably thin, but now they have this significant width, almost like microscopic party streamers. So what did the scientists have to change to go from a skinny little wire to a wide belt? This is where the level of control just gets incredible. It's not just if you use a catalyst, but how you use it. On the left, when you have a very light coating of tiny tin particles, you get thin nanowires.
But on the right, when you use a thicker film of that same catalyst, it allows the material to absorb way more of the zinc oxide vapor, which lets it spread out and form these wide nanobelts. Just amazing.
From 1D wires to 2D ribbons, you know exactly where we're going next. Let's look at a 3D structure that has enormous potential for fields like medicine, the nano container.
I mean, come on, just look at these. They are perfect, hollow, hexagonal boxes, and they just self-assembled right there on the substrate. These aren't just solid chunks of material, they're actual containers. You can imagine loading these up with medicine and delivering it to one specific cell in the body. The potential is just huge.
So how were these made? You'd probably expect an even more complicated catalyst, right? But here's the twist. They don't use a metal catalyst at all. Instead, they grow directly on that mica substrate we talked about earlier. The substrate's own perfectly ordered surface acts as the template, guiding the atoms from the vapor to assemble themselves into these perfect hollow boxes. It's a different process called vapor-solid growth. It just goes to show you that sometimes the canvas itself is the architect.
So we've seen what scientists can build when everything goes according to plan. But you know, some of the most fascinating discoveries happen when things don't go exactly right. Let's take a quick tour through the gallery of nano accidents.
During his research, Dr. Wang found all sorts of strange and unexpected structures, like this bizarre golf club made out of zinc oxide.
And this weird nano fence that somehow formed a perfect little circle.
And even this tin oxide nanowire that, for reasons nobody really understands yet, grew in a perfect zigzag pattern. These happy accidents are just a beautiful reminder that science is as much about pure discovery as it is about control.
But you know, maybe the most powerful insight of all comes from Dr. Wang himself. After he details all of these unbelievable achievements, he includes this quote in his dissertation. He says, "The results show that we are still short of controlling the experiments, understanding the system, and the crystal growth mechanisms remain a challenge." It's just a moment of profound scientific honesty and humility. It's a reminder that even when you're on the absolute frontier, there is always more to learn. So in the end, we've seen scientists acting as architects of the invisible, building forests and ribbons and containers on a scale we can barely even comprehend. The control they have is remarkable, but the potential is really still just unfolding. And it leaves us with one final, very exciting question. If this is what we can build today, what on earth will we architect tomorrow?